Welcome to the Deep Dive, where we explore the most fascinating corners of knowledge. Today, we're diving into a concept that's really captured my imagination. Time is a spectrum of energy. You've sent over some incredible sources, touch on quantum mechanics, cosmology, even black holes. I have to admit, some of it went a little over my head, which is why I'm so excited to have an expert here to break it all down.
It is a mind-bending concept, isn't it? What's so captivating about this theory is that it attempts to connect these seemingly disparate fields and offers a fresh perspective on how they might all relate. Imagine time behaving differently depending on where you are on this energy spectrum, like a river, rapid and turbulent in some areas, slow and meandering in others.
Okay, so let's start with the basics. What exactly does it mean to think of time as a spectrum of energy?
The core idea is that time is not absolute, as we often perceive it, but rather flows in direct relation to energy density. Where energy is highly concentrated, time compresses. Where energy is dispersed, time stretches. It's a paradox where the experience of time becomes relative to your position on the spectrum.
So you're saying that my experience of time here on Earth could be different from someone else's experience, say, near a black hole.
Precisely. And it's not just about feeling rushed or bored, but rather a fundamental difference in how time itself unfolds in those environments.
That's incredible. And you mentioned black holes. Those seem to be a recurring theme in these sources. Are they like the ultimate example of this time-energy connection?
Black holes are fascinating because they represent regions of extreme energy density. Think of them as cosmic whirlpools, where the fabric of space-time is warped to its limits. From the outside, it seems like everything slows down as it gets drawn in. But within that whirlpool, things could be happening at an incredibly accelerated rate. It's like a time lapse on a cosmic scale.
Okay, so black holes are the fast-forward button of the universe. What about the opposite end of the spectrum, where energy is spread out? Does time slow to a crawl?
Exactly. Think of the vast empty spaces between galaxies. Time there stretches out, becoming more expansive. Imagine the faint cosmic microwave background radiation, a whisper from the early universe that's been traveling for billions of years. That's a glimpse into a zone where time is stretched to unimaginable lengths.
So we have these extremes of time, compressed and stretched, governed by energy. But how does this all fit into the everyday world? The sources mention this idea of a color-coded time spectrum. Can you explain that a little?
It's a helpful way to visualize the concept. Just like the visible light spectrum, the time-energy spectrum extends beyond what we can directly see. Each color represents a different energy density and, consequently, a different experience of time.
So it's not that different colors cause different time speeds, but rather that they represent different energy levels that affect how time flows.
That's right. It's a way to map out this complex relationship between energy, time, and even the fundamental forces of nature.
Okay, I think I'm starting to get the picture. But if we were to look at this color-coded time spectrum, what would each color represent? Where would we find ourselves on this spectrum?
Let's start with red. Red symbolizes the slowing down of internal processes and the stretching of universal time. Think of the redshift of galaxies as they move away from us, or the way a cooling star fades to red as it loses energy.
So red is like the slow motion of the universe. And what about those in-between zones like orange and yellow?
Orange represents transformation in moderate energy states. Think of aging stars or the formation of planets. Yellow signifies stability and balance between energy and time, like our sun, a source of constant energy and the anchor of our solar system.
So if red is slow motion, and we're somewhere in the yellow zone, what about the other end of the spectrum, the blues and violets? Those must be high energy zones, right?
Exactly. Blue represents the compression of time and the acceleration of energy processes, like regions of intense star formation or galactic cores. And violet signifies the transition into those truly extreme energy states, think neutron stars or pulsars.
And then, of course, there's black, the most extreme energy density of all, where time seems to halt for an observer on the outside.
Black represents a point where our understanding of time breaks down. It's a domain of black holes, where gravity is so strong that it warps space-time beyond recognition. While time might seem to stop for an outside observer, within a black hole, things could be happening at an unimaginable pace.
So black holes are not just about intense gravity, they're about time distortion on a whole other level. It's mind-boggling to think about.
It is, and what's even more fascinating is that black holes don't just affect time. They actually have a relationship with the mathematical constant pi.
Pi, as in 3.14. What does baking a pie have to do with black holes?
Not baking a pie. Think about the geometry. Black holes, despite their immense mass and gravity, are essentially spheres. And pi, as you know, is fundamental to understanding circles and spheres.
Okay, I'm following you. But how does pi help us understand black holes, especially in the context of time?
Well, we can calculate a black hole's circumference using its radius in pi, giving us a way to measure its influence on spacetime. The surface area of a black hole's event horizon is directly proportional to its mass and energy. And since energy affects time, pi, in a way, becomes a tool for understanding the time-bending effects of black holes.
So you're saying this seemingly simple mathematical constant is connected to the most extreme objects in the universe and their influence on time itself.
It highlights the surprising interconnectedness of concepts in math and physics.
This is already so much to take in. We've gone from colors to black holes to pi, all in the first part of our dive into this time-energy spectrum. What else can we look forward to exploring?
We've only just begun to scratch the surface. In the next part of our deep dive, we'll explore how this theory can shed light on the evolution of the universe, the interplay of fundamental forces, and even the mysteries of quantum mechanics.
This is shaping up to be one of our most mind-bending deep dives yet. Stay tuned. Welcome back to the deep dive. I'm still reeling from our exploration of time as a spectrum of energy. We've already covered so much ground, from visualizing time through colors to the mind-bending effects of black holes.
And there's so much more to uncover. Remember how we talked about the universe starting in a white zone of balanced energy? Well, let's explore how this theory helps us understand the evolution of the universe from that point onward.
You mentioned that as the universe expands, energy disperses. What does that mean for the overall flow of time?
Imagine the universe like a deep breath. As it expands, it exhales, spreading energy outwards, and we shift towards that red zone of the spectrum. Time stretches, things slow down, and that's when we see structures like galaxies and stars start to form.
So it's like the universe is slowing down as it gets bigger. Does that mean we're heading towards a cosmic slow motion forever?
It's a possibility, often referred to as the heat death scenario. But this theory also hints at the potential for cycles of expansion and contraction.
Cycles. You mean the universe could inhale again, bringing everything back together?
It's a fascinating concept. Some physicists have proposed ideas like the Big Crunch, where the universe eventually stops expanding and begins to collapse back in on itself. This would lead to a new point of extreme energy density, a new beginning. Perhaps even another white zone.
So it's not necessarily a one-way street to heat death. There could be a cosmic dance of expansion and contraction driven by this interplay of energy and time.
Precisely. And this is where things get even more intriguing. Each cycle might not be identical. Imagine each cycle of the universe as a turn of a kaleidoscope. Each time a different pattern emerges. Each cycle could have different initial conditions, a different distribution of energy, leading to universes with their own unique properties.
So multiple Big Bangs, multiple universes, each with its own set of physical laws, and maybe even its own unique time-energy spectrum. That's a lot to wrap my head around.
It challenges us to think beyond a linear view of time and imagine a cosmos that's constantly evolving, cycling through different states of energy and time.
Okay, I'm starting to see the bigger picture here. But let's zoom back in for a moment. We've talked about this grand cosmic dance of expansion and contraction, but how do the fundamental forces of nature, like gravity and electromagnetism, fit into this time-energy spectrum?
That's a great question. Each force plays a unique role in shaping the time-energy landscape. Think of electromagnetism, the force behind light and electricity. Electromagnetic waves, including light, travel at a specific speed, the speed of light, which is kind of like a universal speed limit.
Right, nothing can travel faster than light, at least according to everything we know about physics.
Exactly. So in a sense, electromagnetism sets a baseline for time, a cosmic speed limit for how fast energy can be transferred and how quickly events can unfold.
So electromagnetism is like the cosmic timekeeper. What about the strong nuclear force? That's the force that holds the nucleus of an atom together, right?
Yes. It's the strongest force in the universe, responsible for binding protons and neutrons within the nucleus of an atom. And because it operates at such incredibly high energy densities, it could potentially influence the flow of time at the atomic level. Imagine tiny, supercharged time warps happening at the heart of every atom.
So we have these tiny time distortions happening all around us. That's incredible. What about the weak nuclear force? I know it plays a role in radioactive decay, but how does it fit into this picture?
The weak force is fascinating because it introduces the concept of time asymmetry. Certain processes in the universe have a preferred direction in time. Think of it like this. You can crack an egg, but you can't uncrack it. The weak force contributes to this arrow of time, linking energy transitions to the direction of increasing entropy or disorder.
So the weak force is like the universe's one-way sign for time. It dictates the direction of change.
Precisely. It adds another layer to this complex relationship between time and energy.
And then, of course, we have gravity, perhaps the most familiar force of all. It's what keeps our feet on the ground and the planets in orbit. But how does gravity fit into this time-energy spectrum?
Gravity is the ultimate sculptor of time on a cosmic scale. Remember our discussion about black holes? They are the most extreme examples of gravity warping space-time, slowing down time to a near standstill for an outside observer.
Right. So in a sense, gravity is like the conductor of the time-energy orchestra, shaping the flow of time on the grandest of scales.
Exactly. And it's through the lens of this time-energy spectrum that we can begin to see how all these forces, from the smallest to the largest, contribute to the dynamic tapestry of the universe.
This is truly mind-blowing. We've gone from the vast expanse of the cosmos to the heart of an atom, and it seems like every level is influenced by this interplay of energy and time. Where do we go from here?
Well, we've talked about the large-scale effects on time, but what about the realm of the very small? In the final part of our deep dive, we'll venture into the quantum world, where the rules of time and energy get even stranger and more fascinating.
I can't wait. Stay tuned for the final part of our deep dive, where we'll explore the quantum mysteries of the time-energy spectrum.
Welcome back to the deep dive. We've journeyed from the vast expanses of the cosmos to the heart of an atom, all through the lens of this mind-blowing concept, time as a spectrum of energy.
And now we're about to venture into a realm where the very nature of time and energy becomes even more mysterious: the quantum world.
I have to admit, quantum mechanics always makes my head spin a little. But from what we've discussed so far, it seems like this theory of time as a spectrum of energy has the potential to bridge the gap between the quantum world and the universe we experience on a larger scale. That's one of the most exciting aspects of this theory. Remember how in quantum mechanics, things aren't so clear-cut? We have particles that act like waves, uncertainty about position and momentum, and even the possibility of things happening in multiple ways simultaneously.
Right, it's like the quantum world operates on a whole different set of rules compared to our everyday experience.
Exactly. And that's where the energy-time uncertainty principle comes in. Remember, this principle suggests that you can never perfectly know both the energy of a system and the time it takes for that system to change. The more precisely you measure one, the less you can know about the other.
So it's like trying to pinpoint both the speed and location of a tiny particle. The more you know about one, the less you can know about the other.
That's a great analogy. And what's so fascinating is that this principle challenges the notion of time as a perfectly smooth, continuous flow. It suggests that at the quantum level, time might be more fuzzy, more uncertain.
So even at the smallest scales, time isn't as straightforward as we might think.
It seems that way. And this fuzziness of time at the quantum level connects beautifully with the time-energy spectrum theory. If different energy densities correspond to different experiences of time, then it stands to reason that within a quantum system where energy fluctuations are constant, the flow of time might be more fluid, more susceptible to these uncertainties.
So in a high-energy zone, like the blue zone near a star-forming region, time might be more uncertain, more fuzzy than in the low-energy red zone of the expanding universe.
It's a captivating possibility. It suggests that the very nature of time might be different in different parts of the universe, shaped by the interplay of energy and those fundamental forces we discussed.
If all of this is true, does that mean that our everyday experience of time is just an illusion, a sort of average of all these quantum fluctuations happening at the subatomic level?
It's a profound question to ponder. Our perception of time is undoubtedly influenced by the scales at which we observe the universe. We experience time as a continuous flow because that's how it manifests at the macroscopic level. But beneath that surface, at the quantum level, the nature of time might be far more complex and dynamic.
It's like looking at a smooth, still lake, but knowing that beneath the surface there's a whole world of currents and eddies at play.
A beautiful analogy. And who knows, maybe someday we'll have the tools to explore those quantum currents of time and understand how they shape the universe as we know it.
This has been an incredible journey, and I feel like we've only scratched the surface of this fascinating theory. What are some of the biggest questions that still remain unanswered?
There are so many avenues to explore. One of the most intriguing is the potential for manipulating time. If we can understand how energy density shapes time, could we potentially control or even reverse the flow of time?
Now we're getting into the realm of science fiction. But I suppose every scientific breakthrough starts with an idea that seems impossible at first. Are there any current experiments or research projects looking into these possibilities?
There are a few areas where we might be able to find evidence for this. One is in the study of quantum systems under extreme conditions. If we can precisely manipulate the energy states of quantum systems, we might be able to observe differences in how time behaves.
So something like building a quantum clock and seeing if it ticks differently in different energy environments.
It's a simplification, but that's the general idea. Another exciting area is the study of black holes. The more we learn about the behavior of matter and energy near the event horizon, the closer we might get to unlocking the secrets of time distortion, and maybe even quantized time.
Quantized time. Does that mean time could come in discrete packets like frames in a film instead of flowing smoothly?
It's a mind-bending concept, isn't it? And it's one that some physicists believe might be key to reconciling quantum mechanics and general relativity, particularly in the extreme environments near black holes.
Wow, so black holes could hold the key to understanding not just time, but also the fundamental laws of physics. It seems like this theory of time as a spectrum of energy has opened up a whole new universe of possibilities, both literally and figuratively.
It's a beautiful example of how a single concept can revolutionize our understanding of the cosmos and our place within it.
This has been an incredible deep dive, and I have a feeling this is just the beginning of our exploration of time as a spectrum of energy. For our listeners who are as captivated by this concept as I am, where can they go to learn more?
There's a wealth of information out there. Start by exploring terms like time dilation, quantum gravity, cosmic expansion, and entropy. There are fantastic resources available online, in libraries, and through scientific publications. Don't be afraid to dive into the world of theoretical physics. It's a challenging but incredibly rewarding journey.
That's excellent advice. And remember, as we continue to explore the universe and its mysteries, keep those curious minds engaged and those questions coming.
Until next time, keep questioning, keep exploring, and keep diving deep.
This has been The Deep Dive. See you on our next adventure into the fascinating world of knowledge.